Hello, my name is Mr. Pratt and welcome to the next lesson on electricity. This is lesson 16 and we're going to be looking at static electricity. This is a triple science only topic, so if you're studying combined science you won't need to do this one. So for the lesson you're going to need a pen, paper or an exercise book, and unless you're needing to watch this video on your mobile phone, get it out of the way, get it on silent and avoid as many distractions as you can. You'll notice we don't need a calculator today. Some of you will be cheering, some of you won't. We've got no calculations, we're just going to be looking at understanding what causes static electricity. So a starter then, you should have done a little bit of work lower down the school on static electricity, so you should have some prior knowledge. So I'm just going to give you 2 minutes. I want you to think about what might cause an electric shock, explain in as much detail as you can, and then through this lesson we'll be building on that and making sure that we can answer any question about static electricity that comes up. Just approaching 1 minute. If you're struggling a little bit, you should really be talking about electrons. So question 1, that's not a great question. Have you ever had electric shock due to static electricity? Well, I would think the answer is probably yes. Most commonly I get one off my car door when I get out of the car, when I've driven a decent distance and I shut the car door. So what do you think causes it? Static electricity is a build-up of charge, and it can happen when two different materials rub against each other. And when those two different materials rub against each other, one of them becomes charged because electrons are put onto it, and the other one becomes charged because electrons have left it. So we're talking about charge being transferred from one surface to another. What actually gives you the shock is when you've got this charge that's built up on you, and then you touch something that conducts to ground. What will happen is those electrons will start to move very quickly, which gives a small electric current, and that's what the spark is, that's what the electric shock is. If you've absolutely no idea what I was talking about, don't worry, because we're slowly going to build up and explain this during the course of the lesson. Outcomes then. So we're going to try and describe how the static charge builds up. And we're always going to be talking about electrons. I'm going to be saying the word electrons a lot of times during this lesson. And then the other outcome, we're going to talk about this transfer of the negative charges and how it leaves the positive charge, and how that can create a force that might attract or repel two things. Let's try a bit of literal kitchen sink physics then. We're going to have a look at static electricity.
going to get this tap on and try and get a steady stream. This is something that you can try at home. If you can get a steady stream that's quite slow, it works better. That's probably about as good as I can get, I think. Go with that. It's got 3 different plastic rulers. Just try the white plastic one first. Just going to charge it up on me by rubbing it on cotton shirt. Do it 3 times. Let's have a look what it does to that stream. See how it's attracting the stream towards it? If you look lower down the stream, you can see that it's moving. Let's just try giving it a bit more static by rubbing it a few more times. There we go. So it's attracting the water droplet quite a lot. Let's just try it with a clear plastic one. So I've not charged this one up yet, and you see it's not doing anything. Let's charge it up. Straight away. Let's try charging it up a bit more. It's pretty good. Last one. Clear plastic, pink clear plastic. It's one of these flexi rulers. Charge it up. Oh, definitely the best. So try this at home. Charge it up. So you're giving this a static charge, giving the ruler a static charge. There's no charge on those water droplets, but when it's charged, it will attract it. Now, explaining why a charged object attracts an uncharged object is a little bit tricky. It's easier to talk about when 2 objects are charged, so we'll do that first. And later on we'll explain why that happens. Just got some little bits of paper that I've torn up. Again, this paper's not charged. Let's try the pink ruler. Charge it up on my shirt. There you go. So it's attracting the uncharged bits of paper. Just try it with the other 2. White one's not quite so good. It does attract them, but not quite so good. There you go, so they'll all attract them. Just going to go back to the pink one again, just because it works the best. I want you to have a look what happens to a few of the bits of paper when they are attracted to the ruler, but sometimes they fly off. Just have a look at it again, see if you can spot a bit of paper that's attracted and then flies off. We should be able to explain the reason for that later on as well. What I'm going to try and do is charge the ruler, charge one of these up. So I've just got this one bit of paper under here. I'm trying to give this the same, it should get the same charge as the ruler. Should get the same charge as the ruler. Just going to put it down there. I'm going to see now if I can manage to repel that little bit of paper. Nope, attracted it. Let's try it again. Oh, no, it did fly off. One more go. So I'm looking for it to attract and then repel. And it sort of jumped along, didn't it? Okay, I've got another idea where I'll show you a couple of charged rulers up and see if we can show repulsion that way.
Before we can try and explain what's causing static electricity, let's just have a bit of a recap on the models of the atom that we've got. This is the model of the atom, Bohr's model of the atom, where we've got electrons in different orbits there, protons and neutrons in the middle in the nucleus. So electrons have got a minus charge, protons positive, and neutrons have got no charge at all. What I don't particularly like about that model certainly in terms of using it for physics, is it doesn't represent the true scale, the actual sizes of things. So let's swap it for this model. This one is a bit close to scale, so you'll look very small there. We've got the nucleus that's labelled, and it's 100,000 times smaller than the atom itself. And the diameter of those electrons is 1,000 times smaller than that of a nucleus. So we've got the nucleus at the centre, but it doesn't take up much room. Then we've got the electrons that are further away, that are truly tiny and are a lot further away. If I then replace that model with sort of one of my own, if we imagine we've got a racetrack with cars going around it, and the racetrack's 100 metres across, so 100 metres diameter. If we then represent the nucleus with a 1 centimetre P right in the middle of the racetrack, you get a true idea of the actual scale involved and how much space you've got in the atom and how much further away the electrons are than the nucleus in the centre. So in summary, electrons are a lot smaller than protons and neutrons. Electrons are a lot further away from the positive protons that attract them, particularly when you look at the scale of the atom that we've got there. And the nucleus is only 100,000th the size of the atom itself. Most importantly then, electrons are really weakly held to the atoms. They can easily be removed. It's very difficult to take protons and neutrons out, but it's very easy to rub off electrons because they're so much further away and weakly held. You might want to make a note here. These are pretty much the structure of what you would use to answer an exam question on what causes static electricity. When you're explaining it on an exam question, it doesn't really matter what context they put the static electricity into. Your explanation will pretty much follow the same way. So in some ways it's quite an easy question to answer. So I've just put it all up there and I'll talk you through it. So static electricity is caused by an imbalance of charge. Now, charge is something sort of difficult to visualise. What scientists have noticed, and physicists in the past when we've looked at particles, is that there's a force between certain particles. And if those particles have got a force that's the same, they'll repel each other. And if those particles have got a force that's opposite, like a plus and a minus, they'll attract each other. So we've called that thing charge. So when something gets a static charge, the number of positives and negatives is not the same anymore. So on any object, if it's neutrally charged, you might have 2 million positive protons, 2 million negative electrons, and you don't have a charge overall. But as soon as you get extra of one of them or the other, you'll get a charge. So protons are positively charged. That works nicely because we've got P for proton and P for positive. These are fixed though in the nuclei of atoms. So when we're talking about static electricity, we do not say at any point protons are moved. Never, never, never. They're not easily removed. We only talk about changes in proton number and neutron number when we talk about isotopes or radioactivity. Number 3, electrons are negatively charged and they're arranged in shells. That's the Bohr model of the atom that is described in chemistry. But because they're much further away and the forces are quite weak, they can be removed by friction. So when two different materials are rubbed together, electrons can go from one material to another material. So static is, bright red font, always caused by electrons being moved from one material to another. Whenever you answer a question about what's causing static, you are talking about electrons moving from one place to another. That's all you've got to do. If you take electrons away, the material will lose negatives, so it'll become positive because it'll end up with more protons than electrons. If you shove extra electrons on, that material will become negative because there's more electrons than there are protons. So here we've got an example of a neutral object, positively charged object, and a negatively charged object. On the neutral object, we've got equal numbers of electrons, they're negative, there's protons. So on that diagram, we've got 1, 2, 3, 4 positive protons, 1, 2, 3, 4 electrons. Equal number, neutral object. Neutral means not one or another. middle one. It's a positively charged object. So here we've got 1, 2, 3, 4 protons still, but we've lost a couple of electrons. So electrons have been rubbed off, which has left us with a positively charged object. Last one. We've still got the 1, 2, 3, 4 protons. That doesn't change. Number of protons not changing. But now we've had extra electrons. We've got more negatives. So electrons have been rubbed on. Protons do not move when a static charge is produced. Don't say it. Please don't say it. It's always electrons that are moving.
We looked at static electricity attracting things, attracting the stream of water, attracting bits of paper. Now let's have a look what happens to the two materials that come into contact. So we've got friction between cotton cloth and the plastic ruler. Polythene is the plastic that this ruler is made out of. So what's happening now is electrons have been transferred from one of them to the other. I don't know which is which, it doesn't really matter, but electrons are moving. Remember, it's always electrons that are moving. So they should both be charged. If I then hold that cloth, we get attraction. So we're getting attraction from one charged object to the other charged object. Definitely attraction. Pull it back the other way. Attraction. And that's because, let's say it's this way around, that's got a negative charge because it's gained extra electrons, and electrons are negative. That's lost the electrons, so that's now positive. Negative, positive, opposite charges attract, so they attract. Let's now use two rulers. So let's charge both rulers up. I'll just charge this again. I'm going to charge that ruler up. And I'll charge a different ruler up. So they're both charged. But this time, quite strong repulsion. They're pushing away. And that's because they now both got the same charge. They've both got the negative charge. They've both got extra electrons. Let's do it. Should still hold the charge. So it's negative. Push it the other way. Both negative. So we get repulsion. We get repulsion. So if you've got the same charge, you'll end up with those two objects repelling each other. We say like charges, like two pluses, repel, different charges attract.
These three diagrams A, B, C summarise what you've just seen. If you've got, like in picture A, two rods that are positively charged, in other words, they've both had electrons rubbed off, they'll repel each other. If you have, like picture B, two rods that are negatively charged, which means they must have both had electrons rubbed onto them, they'll repel as well. If you've got one rod that's lost electrons, positive, and one rod that's gained electrons, negative, they'll attract each other. Right, I'm going to give you 2 minutes. These questions here will allow you to summarise what we've explained already. So static electricity can cause both attraction and repulsion. So let's just explain how this happens. How do you get attraction? How do you get repulsion? Make sure that you're talking about movement of electrons and what's going on with each one. Okay, 2 minutes. It's coming up to 30 seconds left. So let's talk about attraction first. So with attraction, you end up with one object that's got a positive charge because it's lost electrons, and the other object would end up with a negative charge because it's gained electrons. So in the diagram there, that rod rubbed on that cloth could give you a negative cloth and a positive rod. Those difference in charges will cause attraction. Repulsion then, with repulsion you end up with two objects that have got the same charge. For example, it could be two negatives where they've both had extra electrons put on, or it could be two positives and these objects have both lost electrons. I want you to explain what's happening in this diagram and what will the force be. Will it be attractive or will it be repulsive in this diagram? So I'm going to give you 2 minutes. You might not need quite that long. I'm just going to give you another 30 seconds. I don't think you're going to need the full minute. That'll do. So describe what's happening. So let's have a look. We've got electrons being rubbed from the duster onto the plastic rod, which means that the plastic rod has been left negative and the duster is now positive. So the force between the rod and the cloth, that will be attractive because we've got a positive and a negative. We've got different charges, so they'll attract each other. Let's have a look at balloons then. He looks happy.
So, party balloon, uncharged, made out of rubber. This is actually my 18th birthday party balloon that I kept. So, especially extra woolly jumper on. I'm going to rub it against the jumper. Electrons are going to be transferred from one surface to another. Both of them are going to be charged, and they should be charged with different charges. So that balloon should be attracted to my arm. And it is. Balloon's charged, arm's charged, opposite charges attract, so that's attractive. So the wall up there is not charged. So let's just charge it some more. Put your fingers in your ears just in case the balloon explodes. And see if I can stick it to the wall. almost. I feel the force of it. It's not quite enough to balance its weight. Just give it another go. I'm trying to get it to stick to the wall. So I'm trying to get it to be attracted to something that's not charged. The wall's not charged, it's neutral. Oh, so close. Last go. There we go. I'll be quick. So it's charged, so it's attracted to the wall. Let's assume that the balloon has got a negative charge. It's got extra electrons. So the extra electrons are all against the surface of the wall from the balloon. What those negative electrons will then do, here we go, we've lost enough through the wall. It's still attracted to the wall, you can see it, just not enough to hold it up. Is the balloon's negative, the wall's not charged, but what happens is the extra electrons in the balloon push back the electrons that are on the surface of this wall. Not far, but just enough into the wall that the surface gets a temporary positive charge, so then we get attraction. That's called induced charge, forced charge. So the wall just has that surface positive charge just while you put the balloon there. Now later on you'll do magnetism and we come across that word again, we come across induced magnetism there. So as I put it there, it's just pushing the electrons on the surface of the wall back, and that's enough to give a force of attraction between the two. So that's induced charge.
Let's have a look at this as a diagram then. Got us balloon. Balloon's been rubbed on the jumper. Balloon has got an overall negative charge. You'll see that there's more electrons on that balloon than there are protons. That's the positives. Balloon's negative. When we move the balloon to the wall then, let's have a look now what happens to the charges in that wall. So the electrons now are pushed further away, so the surface gets this temporary positive charge. I'm not keen on the diagram there just because the protons appeared to move and they don't. The protons stay where they are. But those electrons are just pushed further enough away. The wall's still neutral, but the protons, the positive charges, are now left closer to that balloon than the electrons are. So we get a temporary induced charge, and that gives us that force of attraction between the minuses and the pluses. The wall's not charged, but the electrons are pushed a little further into the surface. Balloon is attracted to the induced charge of the wall, and we say that the wall is an induced charge. It's forced. It's only there when the balloon's there. So, another progress check. How would you generate a static charge using the above? Which things have charge and why? And then explain why that balloon will stick to the jumper and to the wall. Don't forget, it's a slightly different explanation when you explain it sticking to the jumper when the two have been rubbed together than you use to explain how it sticks to that wall. You should start noticing there's quite a bit of repetition, which is a good thing. The way that we answer the questions is very, very similar each time. approaching 30 seconds left. Just be finishing off. Just mark your own then. How to generate a static charge using the above. You would rub the balloon on the jumper. Which things have charge in Y? The jumper will end up with a charge and the balloon will end up with a charge because electrons have been transferred from one of them to the other. In the example that I showed you, we talked about electrons being transferred from the jumper onto the balloon to give the balloon a negative charge, which will have left the jumper with a positive charge. Use diagram to explain why the balloon sticks to the jumper. The balloon sticks to the jumper because opposites attract, so they'd attract each other. But the balloon sticks to the wall because the balloon will induce a charge on the surface of the wall. So even though it's overall neutral, the electrons have moved further away. So temporarily, the surface of the wall becomes positive. So we get attraction between the two different charges. A quick look at earthing then, or sometimes it's called grounding. If an object's connected to the ground by a conductor, we say that it's earthed because it's connected to the earth. This means that you can't charge an object up because as you try and charge it up, the electrons will flow. If you've got extra electrons on your object, they're going to flow down. They'll repel each other and flow down to the ground. If you end up with a positive charged object connected to the earth, then electrons will flow up. So only insulators or conductors insulated from the ground will keep a static charge, otherwise they'll just flow to or from the earth. If an earthed object starts to gain electrons, they'll repel each other and flow to the ground, so it'll stay neutral. If the earthed object starts to lose electrons, then they'll be replaced from electrons flowing up from the ground. So earthing a material is a good way of stopping it charging up, and that's quite important in a lot of instances where safety is an issue, where we need to stop static electricity, otherwise we could potentially have a spark and an explosion. We've got a plane here being refueled on the ground, so we've got a tanker connected with that purple pipe which the fuel will flow along. That goes down the wing and then it goes into the tanks, the fuel tanks, which are normally in the tops of the wings near the engine there. But it's earth. We've got a blue earthing cable there connecting the tanker to the metal body of the plane. The plane's been refueled. As well as the refueling hose, there's a bonding cable, an earthing cable. What do you think the purpose of the bonding cable is? Well, let's think for a moment. We've got a liquid, the fuel, octane normally, flowing through that pipe. So we've got a liquid rubbing against the surface of the pipe, which is normally rubber, so it's flexible and waterproof. So we've got a liquid rubbing against a solid, two different materials. Well, let's say then that caused electrons to be rubbed off. So we end up then with the plane getting extra electrons on, and this refueling goes on for half an hour. More and more electrons, more and more electrons, more and more electrons going onto the plane. If that plane was not earthed, we could potentially have a spark between the metal frame and the ground, or even worse, between the metal frame and where the fuel is going in, or to the tanker where the fuel is coming out. That spark could potentially cause an explosion. So the bonding cable will stop the electrons building up on the plane because they will flow back to where they come from to keep both the tanker and the plane neutral. So it will prevent a spark caused by the build-up of static charge. So on these next ones, I want you to describe what's happening and explain why. I'm not going to tell you anything, I just want you to try and work out what's gone on from the picture and explain it. If you started writing about protons or positive moving, cross it out because they don't. "30 seconds left." Right, so if you look at the first diagram, got a balloon. Most of it has got equal numbers of protons and electrons, but on the bit that's closest to the can, we can see we've got extra electrons. And if you count them, we've got extra electrons on the can as well. If you were to charge up that can, so if you rub that can on a different material, you could give it static charge. If you then put that can against the balloon and left it there for a while, you would end up with both the can and the balloon having a negative charge. So if you then just take the can away from the balloon and hold it close, we've got the balloon that's got a negative charge because it's got extra electrons, and the can that's also got a negative charge because it's got extra electrons. You'd have two negatives, so they would be repelled. So the can would be repelled from the balloon. If you think back to the beginning of the lesson, the demonstration I did with the rulers and the bits of paper, I was trying to show a bit of paper that would be attracted to the ruler but then jump off again. What I was trying to do was show you something similar to this. If two objects are touching each other so that they gain the same charge, they will then repel each other. Hopefully at the end of the lesson, when I've got some Van de Graaff generator demonstrations to show you, I should be able to give you an example of that happening there. Just going to give you a minute on this one. Describe and explain. Describe what's happening and then use the physics to explain why. 1 minute. We don't know what sort of charge Garfield gets, so you could answer this question two ways around. It's easier to say this way first. Garfield rubs himself, his feet there against the wool carpet, so we've got two different materials, and by friction Garfield will pick up, let's say he picks up extra electrons, so he will be taking electrons off the carpet, so Garfield will end up negative, the carpet will be less positive. He then jumps onto the chair, and then when he comes into contact with someone that's touching the floor, he's earthing himself, and what will happen is all those extra electrons that are on Garfield will start to jump down towards the earth, and that'll cause a spark. So that spark is electrons transferring from Garfield to the ground. If you decide to say that Garfield has lost electrons, he'll get a positive charge. When Garfield goes onto the chair, because he's positive, electrons will jump to him from the ground. You still get a spark, it's just electrons that are travelling in the opposite direction. So here, just going to look at some of the problems and possible solutions that are caused. We've got a picture of lightning there. If you happen to be struck by lightning, it's a considerable problem to your health, to your life. So lightning is caused by static electricity. Got an old 1970s carpet there. That used to get a lot more shocks in the 70s because the carpets were made out of nylon. I've got 5 things there. I'm only going to give you 2 minutes. I want you to explain what the problem is. So why do vinyl records become dusty very easily? And think about what possible solutions you can have. You might not have time to do all of them, just do as many as you can. The explanations are quite similar for all of them. Got a minute left. You can answer quite a few of these by earthing, but let's work his way down. Vinyl records become dusty very easily because you've got a stylus, the needle, rubbing against a type of plastic material. When one surface rubs against another, you can get static. So if that vinyl record gets static charge on it, it will mean that it attracts the dust out of the air, so it will get dustier. Old TVs used to end up with a lot of dust on the front of the screen as well. So 2 ways you can get around it. You can have, and most turntables have them, a strap which does earth the needle so that you get less charge on there. But really they need to be cleaned quite frequently and you can get cleaners that reduce the amount of static that builds up on there. Number two, come to get a shot for conveyor belt. You've got material going down a conveyor belt. You've got a rubber conveyor belt that's rubbing on rollers so you can get charge on it. To stop that happening, you would need a metal earthing strap so that any charge builds up on it can move away to earth. We've sort of done three. We talked about refueling of airplanes, but it's also the same at petrol stations. We've got fuel moving through rubber or plastic pipe so we can build up a static. You can then potentially get in a spark jumping from the nozzle of your petrol filler onto your car, causing a spark, and if you've got petrol vapor there, you'll get an explosion. So within the pipe that sends the fuel to your car, it will be earthed. It'll be earthed to ground so that charge can't build up. Number four, explosion at flour mills. Then you add lots and lots of flour moving down tubes and pipes or on conveyor belts. You get static, you get a spark. If you've got flour in the air, because flour is made out of very small particles, it will explode. A lump of flour wouldn't, but flour in the air where there's lots of oxygen would be explosive. And number five, highly patterned nylon carpet will easily transfer charge. A couple of things you could do. You could pick a different material for your carpet, or you could get some socks, and within those socks you can have some sort of metallic material which will stop the charge building up. Some socks have that anyway. It can help cool your feet down in hot weather. So there are some socks you can buy that have got like a little woven bits of fine foil within them, and they'd stop the charge building up as well. Maybe a couple of minutes on this 4-mark exam question here. This is often very, very badly marked. Make sure you're talking about the right things moving when you get friction causing static, and then explain why you get that shock. 2 minutes. Just got a minute left. I'll talk you through how I put my answer together, and then I'll show you the mark scheme. Make sure you're self-marking this. It tells us the student walking on the carpet. It tells us the student becomes negatively charged. So for the first bit, explain why friction causes the student to become charged. So we've got to say electrons here. We're not talking about anything else. We're saying electrons are, and then we're going to say where they're moving from. So because electrons have got a negative charge, The student must be getting extra electrons. So the electrons are being rubbed off the carpet onto the student's socks, and electrons are negative. So it's 1 mark for saying that the electrons are negative and 1 mark for saying that the student is getting extra electrons. They're getting rubbed onto the student's socks. Second bit. Some carpets have thin copper wires running through them. The student is less likely to receive an electric shock after walking on this type of carpet. Suggest why. So copper wires are conductors, so they'll conduct. So if you imagine the students walking on the carpet and the electrons are being rubbed onto the student, what will happen is that the electrons will be conducted along those wires, stopping the charge from building up. So I'll stick the mark scheme on and you can have a look, give yourself a mark out of 4. Transfer of electrons, 1 mark. From carpet to student, 1 mark. Carpet as a conductor, now 1 mark, or copper as a conductor. And less charge or no charge building up. Going to leave you with a summary then. The bottom right, we've got like charges repelling and then unlike charging attracting. We've got examples of how you get a neutral, positive charge and negatively charged object. And then those 4 key points there allow you to answer pretty much any question, explaining protons don't move, it's electrons that are moved during the friction. That gives you the static. If something's negative, it's got extra electrons. If something's positive, it's got electrons missing. Okay, well done for working on that. We've got 1 more lesson on electric fields and static electricity, and then that'll be the last one in the electricity topic. So I'll see you next time.